And we are live here from the Worcester Lab. It is I, the alien scientist, Jeremy Riss. So those who don't know me and are new, I just want to let everyone know I have a degree in physics from Bridgewater State University. I graduated in 2012 with a degree in physics, minor in math. I've been studying this stuff ever since and all through high school. So been quite a ride, learning everything I can about alternative propulsion, warp drive, electromagnetism, the whole reformalization of Maxwell's equations with the Heaviside and Gibbs formalizations, all the Bandurix stuff. We've interviewed tons of scientists. We interviewed Mark McCandlish on the first APEC before he died, and we've interviewed tons of scientists on this channel through the APEC conference in conjunction with Tim Ventura and all the APEC scientists. We've brought together an awesome team from the public to bring research and collaboration within the community. And it's just great to see that science is now progressing at this rate where, you know, something can happen on the internet and it rips across the world and takes it by storm. And how convenient was it that we had just got this vacuum furnace about 2 or 3 days before the weekend before? It was like Thursday or Friday before the LK99 announcement happened from South Korea. And by the way, we got people from South Korea in the audience watching right now. This is awesome. Just want to shout out, if you're in South Korea, just put a number 5 in the chat so we can know down below. And wherever else you're from, Pennsylvania, just shout out where you're from in the chat, and we'll give a shout out to you. Love from the UK. We got people from worldwide watching. So yeah, and that's what we did. We said, you know, when this stuff's going around, we have everything here pretty much to do it. We're a well-equipped lab. We just got the vacuum furnace, which is like the big key to doing all this. So we said, hey, why not? We can find out ourselves. We can follow the recipe. There's a recipe here online, right in the PDF, if anyone's read the paper. And it's got a 3-step process for how to create the superconductor, or how they created the superconductor. And I'm going to have Jan over there hide some of our proprietary stuff because he's working on some of we have some other reagents we're going to try mixing up a little bit differently, some of the same arrangement of chemicals, but a different chemistry mixture to try cooking. Just to some of our material scientists on our end are looking into this and stuff, and also asking our AI, which we've trained with our own databases, kind of how to do this. And there's what's with the idea that the team. So I got to get Michael over here. So I want to introduce our head scientist here at the team. He's from WPI, and his name is Michael Perrone.
Hello.
And
we're live.
Oh, that's good.
Yeah.
So,
Hey, Jeremy.
hello, this is Mohammed.
Yeah.
Hi.
What's going on, man?
Doing good.
Yeah. So yeah, we just got these alumina crucibles to formally replicate the experiment exactly as the paper says. Although there's some there's a little bit of variability in what it says about how much copper phosphide to add relative to the lanarkite.
Well, that's a finer detail. Let's start at the basics. We got high school kids watching. We got grandmothers watching. So let's just try to take it from step 1 and talk about what we did for the first. Let's go back to what we did first.
So our first synthesis, we had this graphite crucible. We tried to coat it with boron nitride like this to prevent it from reducing the lead out of solution. But unfortunately, it's all stuck to the bottom, but there are chunks of lead from that first round. And the boron nitride just flaked off. So boron boron nitride coated graphite won't do it. We had a second test, which was silicon carbide. I'll go grab that one.
Yeah, the silicon carbide test, and then we just cast some molds of to make our own crucibles over here. We used some plastic cups. I used these smaller clear plastic cups placed inside the big red party cups with
yeah, Cotronics Ceramic. It's a good company. But anyway, yeah. So we got this graphite crucible we made.
This
we
one's graphite.
didn't have formal alumina crucibles at the start of this whole thing a week ago. So now we have those. We can run 4 batches a night with alumina. But yeah, you can see over here, if you get the lighting right, it's red. That's all metallic copper. So the silicon carbide appears to have, there's like a glassy interface at the edge between the silicon carbide and the lanarkite mixture, and that's all metallic copper. So we had hoped that the silicon carbide would not reduce the mixture, but apparently it crashed a lot of copper out of solution. Also, this has been used for previous experiments, so there may be contaminants that we, well, it's possible that it's contamination that the ones we found earlier. So we're tracking that down. We have another batch which is made in the alumina crucibles that we made with the Cotronics material. These have excess copper phosphide, so they have a lot of metallic copper at the end of the run too, which is the red color. The reason we're adding excess copper phosphide is to see if we can produce more lanarkite in a run, because the actual copper phosphide does not have a lot. Well, it doesn't have enough phosphorus to convert all of the lanarkite into the oxypyromorphite phase, which is the actual superconductor, purportedly. So there's just a little bit of phosphorus in there. There's way too much copper, so they're going to have excess copper, and there's way too much lead as well. So it seems like these crucibles, due to the yellow coloration of the walls, they may have. What are you doing, Jeremy? Okay, yeah, the yellow coloration of the walls. The phosphorus. I'm sorry. The lead probably soaked into the pores on these alumina crucibles.
The camera's right here, so I'm just...
Yeah, I got you. But anyway, yeah. So I mean, you got this. You have this material kind of leaching into this, which isn't ideal. So now we have actual alumina crucibles, and hopefully that won't happen with these. It seems at least that the material detaches easily from alumina. So it's hopefully we'll be able to reuse these crucibles for multiple runs. Probably has a different thermal expansion coefficient. Anyways, the oxypyromorphite phase is liquid. Actually, maybe we can see it here. No, not really. But yeah, I mean, I think the article, and I may be mistaken, but it looks like they're trying to go for some gas phase processing so that the lanarkite is substituted with the phosphate and the copper. But I mean, the actual material is liquid when it's in the furnace. You can take a crucible and tilt it and then start the furnace again, and it will slump into that area. It flows like a liquid. So, which makes sense because pyromorphite in Greek is pyro, fire, and morph, which means to change. So the Greeks knew that you could take pyromorphite and melt it and reform it, and it would recrystallize. So that's
So you can take a seed crystal of what we got already and try to use that to grow more stuff? Is that
not at the moment? No, we're just still running various tests. So, I mean, this is good info. Graphite will reduce the lead out. Silicon carbide will still probably reduce a lot of the copper out, and there's some reaction at the interface here. So not optimal materials. Alumina is indeed the ideal material for this. Unfortunately, this batch that we ran last night doesn't exhibit superconductivity, so we're going to have to toss it in there again and remelt it, I think.
And what about the vacuum? Like this was done, they did a process with this vacuum tube, like over here, where they we had been set up to do this in a smaller furnace. If you didn't have like a vacuum furnace, that's an $8,000 furnace over there. So,
yeah, if you can pull vacuum on a quartz or borosilicate glass tube, then you can blowtorch ampules off of that and fill them with material, and then you can put it in a normal furnace and try the same experiment. It works well enough. It's just we're missing a component for our system. We were actually going to make some vacuum tubes for a separate experiment, so we had all this set up, but we haven't been able to use it for this one yet, unfortunately.
And that's the this is the way that the other replication that we're seeing on Twitter is doing it, with like this. So that's what
Yes.
other people have seen.
Yeah, and that's probably a better way, to be honest, because you don't want to foul up your vacuum pump with all of the, because you're going to have sulfur coming out of this. Basically, it's a bit of a mess, to be honest.
Yeah.
So if you can pull vacuum on a tube and then just keep the whole thing contained. And then on top of that, that's better because if you put in the right stoichiometry with the phosphorus and the copper, you're not going to lose any in that sort of experiment. So it's quite controlled conditions. That's a good way of doing it. I mean, we're going to run a whole bunch of different things. Another thing we're going to try tonight is just mixing up the proper stoichiometry without the we'll try with and without a little bit of lead sulfate, because we think that the lead sulfate may be helping the material to crystallize. It might nucleate crystal growth, because if you just have, if you have pure pyromorphite, it should crystallize. In theory, it shouldn't just form a glass. But this is oxypyromorphite, so it might be slightly different. We're wondering if we'll get a lead glass, basically. But I mean, that's something to try. It would be a lot easier to just not even deal with the lanarkite and just melt it into a solid phase that recrystallizes because it's pyromorphite. The copper added may make that difficult. That's what I'm thinking. It might just form a glass. So I mean, the lead sulfate eventually, the sulfur gets reduced and evaporates off and replaced by the phosphorus, and that's kind of how it happens. And this is like how geology happens in the earth, like how metamorphic rocks form. So you're getting this substitution reaction. The phosphorus goes in, the sulfate gets reduced, and the sulfur leaves, and then you have these crystals forming inside the lead sulfate. And apparently melting off because the melting point is low enough in here, and that probably helps recrystallization. It's like right at the melting point, just about.
So let's take it back, because I asked for a high school explanation. We get a graduate level explanation from Michael all the time. And I want to break it down for my audience, because we have a lot of people that are watching. We have actually PhDs asking like high level questions, which I'm going to get to.
We should answer those.
Yeah, maybe those would be more important to get into than dumbing it down. But yeah, I wanted to talk a little bit about the process and some of the reagents, but I don't want to give away some of the secrets of what we're going to try as well.
Well, I mean,
unless you're willing to.
There's no real secrets here. I mean, there's a list of metals that form. We can get a sequence. There's a list of metals that forms +2 ionization states easily, that are slightly smaller in atomic radius than the lead. So that list is fairly short, and they pretty much have all of them in the paper. So for example, they have silver and nickel, and tin and stuff like that. So one of the things we found is we were able to get small, very, very small pieces of lanarkite, even without making the what do you call it? We didn't actually have to make lanarkite. We just mixed the lead oxide and lead sulfate, and we still got some small crystals that exhibited these properties. So it's not. I mean, it's a molten phase anyway. The lanarkite is still solid at the temperature ranges we're talking about, but it's at the interface with the liquid phase where this thing is going on. So you're getting some. I don't know. I think you might not need to make lanarkite to make this stuff. As long as you have the sulfate and the lead oxide and it dissolves in to the lead phosphate mixture, you should get
Lanarkite's
at least
like
some
step one.
lanarkite. Well, yeah, lanarkite. But so what I'm saying is, like, for people who are trying to prove out the concept, we've skipped that step and we still got stuff that appeared diamagnetic. We have a bunch of pieces now.
Yeah.
So, I mean, the yield isn't great. I imagine crystallizing the lanarkite phase probably increases the yield because it creates more nucleation sites for crystal growth. But you don't have to.
So esoteric gold, did you use an inert gas or a vacuum when heating? So I know we have argon. Did we ever?
So far we've used vacuum. So 10 to the negative
vacuum.
2, 10 to the negative 3 torr, just about. So just like a lot of the other applications.
Yeah, we have a vacuum furnace.
Yeah. So, I mean, it has the capability to run argon, but we haven't set up the tubes for that yet. Any other questions?
He'd use argon gas. Okay.
Powdered gold with the,
Yeah. So we were talking about that processes.
Few smaller pieces of LK99. Oh yeah. So this is what I was saying earlier. LK99 is a oxypyromorphite phase, so that will melt and reform crystals. It'll grow nice crystals. The other phase I'm looking at is vanadinite instead of oxypyromorphite, because vanadinite, in theory, should also melt and form nice crystals, albeit at higher temperatures. It's easier to keep the stoichiometry correct, though, because it's the vanadium centers, unlike phosphate, vanadate doesn't evaporate at low temperatures. So here's hoping it's easier to make a vanadium analog of this material. Otherwise, vanadinite has the same crystal structure as this. The trick is vanadinite has a chlorine atom, and I think the chlorine or a natural pyromorphite won't superconduct, is my guess, because the fluorine and chlorine and all those, they don't have the same spin properties as oxygen does. Oxygen is very important in other superconductor phases as well. So I think it needs to be oxypyromorphite and not natural pyromorphite, because the chlorine and the fluorine will kill the superconductivity. That's just a guess, but an educated guess. So vanadinite has the chlorine, so we have to make an oxyvanadinite phase, if that's even stable, and see if that works.
So whether it's legit or not, Nate, remains to be seen, because it might just be diamagnetic material. So we have to wait until we get a big enough piece
to 4-point probe
so that we can 4-point probe the thing. Let's go and show the 4-point probe. We did a demonstration of this the other day. Just working too well. I think I'll get an actual. Let's try it again.
We need to clean up this.
It would be nice to try it again, but we showed.
Anyway, yeah. So we got a Keithley DMM 6500. This thing will go down to like nanoamps of current and crazy stuff like that. And this is plenty sensitive for testing superconductivity. Let's not.
I don't just wanted to show it off.
Oh yeah. We have liquid nitrogen down there, but
and we have
we want that to last the week, hopefully.
Yeah.
So.
but we had these sample superconductor YCBOs so that we could as test probes. So right here, the test probes that we got.
Yeah. So these have
4-point.
these have silver attachment points for 4-point probing, and we'll get an actual 4-point probe and we'll test it with that, because these normal probe tips are not good enough to test superconductivity. They're nickel plated. You really need gold plated tips to test superconductivity well. So, and these aren't even the right type. Like you can get really good 4-point probes that have 2 tips in one of these devices, and then you just have 2 instead of 4, and they're a lot easier to handle. But yeah, so we have the 4-point probe test ready for when we get big crystals, but that'll be a while because we're testing a whole bunch of stuff first. I think we'll make a vanadate analog instead of phosphate. See what we can do with that. I mean, it'll be much easier to form large crystals, much easier to maintain the stoichiometry under vacuum. You won't have like stuff evaporating into the vacuum pump, which, by the way, we should change the oil on that.
Yeah, let's change the oil in the vacuum pump. I think the next run that we do with these 4 alumina crucibles that you got, the new ones.
So we'll test the vanadate phase.
Esoteric Gold suggested that we
put argon
in the chamber too, and then
we'll need to make sure we have we'll need to make sure we have the right tubing to attach to it.
Yeah, I can get that figured out.
Okay. So, I mean, we can try argon. Shouldn't make a difference. It will certainly slow down the evaporation rate, so you'll retain more phosphorus for less copper. So that's a desirable feature. What else did we want to test? Other phases. We got a recommendation to try nickel. There's tin. There's a bunch of other. There's bismuth, but bismuth, it's hard to give it a +2 oxidation state to replace lead in this context. So that one might be tricky to get to work.
All right. I want to show from this angle those crucibles.
Oh yeah, I mean and the other thing we're testing is just different ratios of copper phosphide to lanarkite, or to lead oxide and lead sulfate, depending on how we do it. Since it's a molten phase process, it shouldn't really matter too much that the lanarkite is there or isn't there. And honestly, since we're baking at a higher temperature, lanarkite should form faster out of the lead oxide and lead sulfate.
Yeah.
Assuming the sulfate just doesn't immediately come off and evaporate off. So, we'll probably do a couple batches with actual lanarkite again at some point, just for comparison. But yeah, I think our most successful test so far had about 2.5 grams of copper phosphide for 10 grams of lanarkite, which that's over the stoichiometric amount for the copper, but it's under the stoichiometric amount for the phosphate. So you'll still get a lot of unreacted sulfate from that. Anyway, yeah, that's about it.
All right. Any questions? Please put them in all caps, and we'll try to get them answered. I just want to show the inside of this furnace because it's cool to.
Yeah, we got this special made for producing. What was it again? Calcium aluminate electride. The ceramic material goes up to 1750 continuous instead of the usual 1700. Just because you need that little extra amount of heat to get the calcium aluminate electride to melt.
So what do you think? Do you think this superconductor is legit?
I think there's a good chance that our silicon carbide sample was contaminated, which is what we got for results. But some of the chunks definitely don't look contaminated. I mean, they just look like a chunk of some ceramic. So, but it's hard to tell. It's opaque. So, one thing we will definitely try is we'll take the pieces we've got so far and we'll put them under SEM and see if we can get a specific we have SEM with EDS, and we can check the chemistry of it to make sure it's not just a chunk of iron or something that got in.
Yeah, that would be a good step to do first. And but it looks promising so far, man. That piece that we showed on the video earlier, I might find that video and share it.
We actually have a few that look even more interesting in terms of diamagnetic properties.
Can you post them on the drive?
We'll film them a little bit later because you got to go through the microscope because they're tiny.
Yeah. All right. Let me see what I want to play this video. Anyway.
Oh, is that the one? Yeah.
Yeah, I'm going to play this one. And guys, I noticed some people left super chats. I want to thank everyone who left a super chat. All that's very much appreciated. I actually tried to launch memberships on my channel, and I'm going to start doing memberships. So if anyone is interested in becoming a member to my channel, that would be awesome. You can be the first one, and be happy to shout out those as well. So here's the video.
I expect Jeremy to help me clean up this lab when we're done.
Oh yeah.
Yeah, there you go. There's another chunk of actual magnetic material that eventually you see. Yeah, you see it being dragged by the magnet.
Yeah. So
the interesting thing about this chunk here is the torque is being applied by the magnet, but it doesn't get pulled by the magnet, which looks a lot more like diamagnetism. And you can compare it to the effect of the magnetic particle that's there. Very straightforwardly, it's
yeah, it's pulling around. See, like the thing is, right? If it were just a ferromagnetic impurity in the tip of that, say, like it would move around more similar to the way that other piece is moving around, but just in the direction with the tip there.
Oh, it's starting to play another thing.
Yeah, let me just. Oh, where's my thing? Hold on. All right, so let's go back and just play it again, so you guys can see the way it's moving around on there. It's not like sticking to the magnet and following it around like a piece of ferromagnetic wood.
I mean, it's always possible there's a small ferromagnetic impurity in that chunk, but yeah, it is strange. Yeah, I mean, more tests are on the way. I mean, there seems to be a lot of other people who've made floating bits, and yeah, we'll try more things. Yeah, I mean, here's hoping that we can just melt the pyromorphite, the oxypyromorphite phase, and recrystallize it without the lanarkite. I mean, I think that's a excessive, like, it's an extra step that we might not even need. Here's hoping, you know. Is it still live?
Yeah, it is.
Why are you on here?
Because this was the thing. I don't think I've fully launched this. But anyways, I don't know. I thought I launched the memberships earlier, but it's not turned on my channel because people were saying I can't. They couldn't figure that out.
Well, anyways, we can do that later.
I'm going to do that later. We'll set that up
starting
later.
Some other video now.
It's starting another video now on this. Forgotten Giants of the LK99 Observatory. But anyways, we have some more videos. I guess I can play the other videos too.
What? No, I mean, this is fine for now. I mean, what else is there?
I just took another one on here.
Whatever. Oh, that's the earlier video. Yeah, but that's not as obvious, you know, because
yeah,
I didn't have enough hands to move the paper around.
Yeah. Yeah, you couldn't hold the camera on and do it at the same time.
Yeah.
But does it stop being diamagnetic if we heat the sample? That was the question.
That's a good question. We need to try that.
So let's try that. Let's try that. Can we do that right now?
I mean, probably not on a stream. It's like you got to have the camera there. You got to be like,
Jan
it's very finicky.
You. But
maybe.
Yeah, maybe.
Let's just do that and post it afterwards.
Yeah, we'll try that next. And
can we buy samples Well, I mean, I think we'd have to license the patent first in order to sell samples. But I mean, if someone can get us in touch with the team that's making the stuff, sure.
Yeah,
We'd license
yeah. I
that
don't know
patent.
what that's going on with that because yeah, I'd be happy to license the patent for them and make samples for
Well,
other
it sounds like
labs.
there's a
But
little bit of political BS going on in that group. So I don't know. Hopefully they figure it out so that humanity can use this thing sooner.
yeah, so we could. I have some magnetic field paper too, like he's talking about.
That's neat.
The magnetic field film.
Yeah.
Wow, where the heck do I have that piece? It's somewhere in my.
What other? Let's see. What else are people saying?
Yeah, the situation's learning a better recipe.
Well, we're trying out a couple things here because first off, the lanarkite takes a long time to make. So does it work without the lanarkite? I think the answer appears to be yes. It can work without the lanarkite. The other thing is we didn't have the alumina crucibles, so we figured we might as well try other crucibles, and the other crucibles did not work very well. Any reducing material like silicon carbide or graphite will pull the copper or the lead out of the melt.
Yeah.
So you have to use an oxide crucible. If not alumina, then maybe zirconia. But basically, we're getting as much useful information for people as we can with the materials and hardware we have available. And then the oxypyromorphite phase. Can we just generate that itself without lanarkite at all? And stuff like that.
Yeah.
These are the experiments we're running. Oh, there's something in Korean. Let's translate it.
Yeah, I wish we could get a translator on this these comments.
Well, it doesn't have a question mark in it, I guess, so maybe it's not a question. Anyway,
we'd love to have someone in South Korea who could get in touch with the original team and do some questions, because I know there's been a couple other replications online for the LK99 stuff. Most famous on Twitter is Andrew McCalnip of Vardaspace.
Yep.
And so Andrew, I know he put a list of good. He's doing great work, and we've been following him as well. He came up with an excellent list of questions. Maybe we could expand on that list.
Where's his list? Let's see it.
Yeah, so I'm gonna find that on here. I know I liked it, but let me see if I can't share this screen too, so that people will be able to.
One thing, while Jeremy's figuring that out, the other thing we've noticed is it's a lot easier to smash up the sample and try to pick out a piece under the microscope than to make a macroscopic crystal. It looks like it just takes a long time to crystallize, relatively speaking, or maybe it takes a long time to diffuse. So yeah, people are trying all sorts of different things, using a lot of copper phosphide, using a little bit of copper phosphide. Yeah.
He's got a nice magnet. That thing's dangerous.
Oh yeah.
Where the heck did he say? Yeah. So here's
here. Yeah. Precursors. What level of purity is required? Don't know yet. Are there any necessary preparatory steps?
In the thermal steps, we had a question about the ramp time, the ramp down. Did we quench or did we slow cool?
We slow cooled.
Okay.
That's a good question, though. I mean, slow cooling in theory should generate larger crystals, but it may also relieve internal strain in the crystal structure. So it's a good question. It's an open question as of now. The level of purity required, we just hit like 99.95 on our stuff, if that helps anyone. Keep an eye on those questions. I can't read those from here.
Sorry.
Let's go through them. So let's see. The necessary preparatory steps. So as I mentioned, it seems like you don't necessarily need to make the lanarkite. It looks like you can go from lead oxide and lead sulfate mixed together, because at 900 C, they mix a lot faster than at 700 C. So the generation of lanarkite crystals in that larger set of material happens pretty quickly when you just mix everything. That said, the copper phosphide does release phosphorus pretty quickly as well. So it will probably boost your yield if you prepare the lanarkite first. But if you're just trying to get a tiny chip to look at under a microscope, you can probably skip that step reasonably. What's the environment? Air, vacuum? We've been using vacuum. A lot of the people who have been testing it have been using vacuum. If you use air, you will over-oxidize the lead. The lead's in the +2 oxidation state. You're going to go to the +4 oxidation state of the lead. Or you'll just evaporate a whole bunch of stuff out of there, or burn it. So you need it to be vacuum because you don't want the oxidation state to go too far. What is the temperature ramp up and ramp down? Yeah, we mentioned that. Thermal annealing steps. Again, we don't know whether that works or hurts in this case. Because you have a strain in the lattice, which that's probably helping the superconductivity, and annealing could remove that strain. So how sensitive is LK99 to the duration of the 925 step? I would say pretty sensitive. The paper said 10 hours. I found 7 to 10 hours is a good range. As the paper said, if you go over 10 hours, like especially over 40 hours, you lose all of the lead sulfate. The sulfate ions come off and as sulfuric acid and sulfur oxides and stuff. Well, mostly sulfur oxides. But anyway, the lead sulfate breaks down eventually. So if you need that to crystallize, to nucleate crystal growth, then you don't want to bake it for too long. Under 5 hours, just like the paper said, you pretty much never see anything. There hasn't been enough crystallization and mixing and stuff at the 5 hour mark. So, but yeah, I would say 7 to 10 is probably the optimal firing range. As for results, elaborate on differences between bulk material and the thin film.
Yeah, can it be made in bulk?
That's interesting. So, they were saying that you can vapor deposit it once you have the final crystal structure. But if you can vapor deposit it, then why not just mix up the oxypyromorphite composition as a glass and then use that as like a sputtering target or a vapor depth target or a vapor depth source? I mean, so they said that it can be used as a vapor deposition material. So I think people should also be trying to simply mix up oxypyromorphite stoichiometrically. And then if you have a vapor depth machine, you can try firing that up and evaporating some of this stuff onto a surface. And it should it should crystallize quite nicely under those conditions. But I suppose it's also substrate dependent. What you're evaporating onto will depend, will affect whether it actually makes a superconductor. So actually, considering they used lanarkite, you could produce some lanarkite and then use that as a vapor deposition substrate to produce a thin film. So that's an idea people should definitely try. Vapor depth should work very well for making high quality crystals. Okay, go back to the questions.
Great, good, cool researchers.
Yeah,
that was the comment from
nice.
Korean. Thank you for Brian Kelly for translating for us.
Hey, cool. Thanks, Brian.
Good to see you here, Brian. Memes of Destruction is still in the audience.
Hey, look, it's echoing. Your audio's off. You don't see the comment? It's right there.
Yeah, but it's just it's audio. So I'll mute that screen audio so that
there you go. If you have multiple screens here, okay.
Yeah, so that should not echo now. If it was. So
let's see what else we got here.
If I want to
measure the resistance. Oh yeah, we're not going to measure the resistance anytime. Well, so we need to make a large enough crystal to do that, and that's going to probably take days. Right now, we're just experimenting with optimal compositions and different process parameters to help in the efforts to replicate this material better. and trying to see what's really relevant for getting the best results.
So where's the pieces you've got so far?
Oh, they're just in the tiny.
They're super, super tiny.
Yeah, they're like dust grains basically. Yeah, you can kind of make it out though. There's like a handful of them in there. Like,
Yep.
we got like 5 pieces so far.
It's going to be quite expensive per gram so far.
No, I mean,
What do you think
I'm
about the
guessing
production on
there's
this?
probably
It's like-
way better synthesis routes.
Right.
But if we're just trying to find compositions that work and we're skipping the lanarkite step, that's still not that bad. So let's go back to that scientist's
So
questions
for a
on Twitter.
4-point probe, I think we need something that's at least half a centimeter in square, like something like about like I don't know. What
A couple
do you think?
millimeters is fine.
A few millimeters.
Like if we get high quality 4-point probe tips, the probes themselves are spaced like a couple hundred microns apart, so you can get a smaller crystal. But yeah, I mean, I would definitely say the superconducting phase looks almost identical to the sulfate melt at times. So it's really hard to tell what you've got your probe tips on. And I wouldn't be surprised if the partial resistivity that they measured in some of the earlier tests was from some pieces of sulfate that were included into the superconductor, or even contacting the 4-point probes they used or something.
Well,
Let's go back to the questions and let's go to the Twitter questions that scientist had. See if we can answer those, because that's productive. Here,
yeah.
Go back.
So the other guy there.
I think it's that one.
Let me just back. Yeah.
Yeah, there we go. Okay,
This is Andrew McCallop, by the way.
McCallum.
McCallop. Yeah. No, there's no N in there. Okay, so Andrew McCallop is one of the scientists on Twitter who is replicating the LK99 in his lab. So we were just reading some of his comments and questions to the Korean team.
So let's see. We can probably answer some of these from our experiments so far. So that's what I was doing.
He probably answered a lot of these himself because this was July
Probably.
31st. So
He's probably been doing this for a while then. But in any case, how repeatable is the prescribed recipe? Well, yeah, stochastic. That's because the ingot that they're making isn't just the superconducting phase. There's other phases in there, and if your like copper doesn't diffuse properly into the rest, then you're not getting the right phase throughout with the right dopants. Perfect. We have our copper phosphate ready to react with the to try and make the direct. So we'll try and make the oxypyromorphite phase directly without lanarkite and see what happens.
Wait, hold on. Show that. I want to full screen this.
It's just some lead phosphate, I hope. It looks a lot like copper hydroxide, so I'm hoping it reacted. But yeah, we will try that and see what we get. And we're also going to try to make a vanadate phase, which is identical except it has vanadate instead of phosphate. And then you don't have to worry about phosphate or sulfur evaporating or sulfate evaporating during your runs at vacuum.
So I showed the video on the channel already. You guys can. We're going to do more tests because I want to try to heat it up under the magnetic field and see if it loses that diamagnetic effect as you heat it up.
Nathan, it's not clickbait. It's well, I mean, it's a partial success. We see some diamagnetism apparently.
Yeah, it's not it's not misleading at all, man.
This is the nature of science. You keep getting more data, and you don't just get the answer handed to you or whatever.
Yeah.
It's incremental. This is incremental.
But a couple of labs saying they didn't get anything at all. So I mean, we got something. So it definitely looks just not like a normal, contamination or something. It's definitely something. I mean, these pieces do weird stuff under the magnet. You've seen in the video, and I watched it firsthand. So
let's keep the focus on those scientific questions, and then see if anyone else has some scientific type questions in the live chat afterwards. But come on, back to the.
All right. Let's go back to Andrew's.
Yeah.
So
There we go. Let's finish this up.
what type
No,
of
no distractions. So let's see. The bulk material in thin film, stochastic. Again, the stochasticity is due to the different phases involved. There is a superconducting phase, and there are non-superconducting phases in the ingot at the same time. So could you provide details on equipment? Okay, so that's more of that's going to have to be the other two. Thin film deposition, glass substrate. I would personally use the lanarkite if that apparently nucleates the crystal growth. That would be an excellent vapor depth substrate. Just prep a bunch of lanarkite and then vapor deposit onto the surface of that. So the exact set point temperatures of the tungsten boat. Well, I mean, that one's easy enough to just scan through, to be honest. Interesting. Yeah, I would definitely go above 900 C to get vapor depth out of this stuff. The phosphate phase seems pretty stable at 925 C as a liquid. It doesn't seem to evaporate in any reasonable rate. So you're probably going to be more towards the 2000 C end rather than the 900 C end to get real evaporation of the phase. And then the patent, that's a good question. I don't know the answer to that one either. All right, let's go see if there are questions in the comments.
Yeah, let me just see. There's a lot of comments. We got like 250 people watching. So,
all right, let's pick through it. Why are you confident vapor depth works? I'm confident vapor depth would work because if you deposit onto lanarkite specifically, it will nucleate crystal growth. So what's happening in the crucible is the copper phosphide is decomposing and the phosphorus is contacting the lanarkite surface from the vapor phase, and it's reacting with the lanarkite to replace some of it, and that starts the nucleation that starts crystal growth nucleation. And within those temperature ranges, oxypyromorphite is a liquid, or at least this phase of oxypyromorphite that's heavily copper doped is a liquid, and that liquid will form on the surface of the lanarkite, and the lanarkite should induce the crystallization of the phase that we want. Now, if you're doing this from the vapor phase, you're not going to have liquid on the surface, but it should be a catalyst for getting the right crystal phase still. If you have nice fresh lanarkite crystals. Yeah.
Purity, issues of purity, because we're touching these crucibles, not wearing gloves. Sometime,
any of those skin oils are going to evaporate off way before we really get big thing go. But yeah,
other contamination and what.
So yeah, I mean, we did 99.95. I think we have 99.99 on some of our materials. Some of it's lab made though, so that's a big question mark that gets thrown in there. One thing is some people that had extremely pure samples did not get positive results, and that's probably because they didn't have the copper sulfide impurity that was reported in the papers. I would not be surprised if the copper sulfide phase plays some additional effect. I imagine that if you have the oxypyromorphite, you will probably want to have some percentage of the oxygen substituted by sulfur or even selenium. Maybe even tellurium, but that's a bit much probably. What else do we have?
Yes, so people who got here just now, we're talking about the finer details of the science of this superconductor replication of the LK99. So we tried some in our lab last week, and we finally got it out of the oven and got some pieces that look like they're diamagnetic. I showed those on the video earlier. I can show that again.
So the vacuum we're using, by the way, is 10 to the negative 3, like 10 to the negative 3 torr or something. It was, well, whatever it was. It's fairly hard vacuum.
It's not turbo pumped, but
it's not like diffusion pumped or turbo pumped, but it's a nice efficient scroll pump. Can you go back to let's scroll through the questions a bit, because it looks like
I'm going through the questions.
So right at the bottom. Okay, so planning to evaluate the purity.
But yeah.
So we have SEM with EDS. So whatever our best crystal phases will be, we'll take whatever appears the most diamagnetic and we'll put it under SEM, and we'll see what phases we get with what compositions. I mean, the EDS we have is not super sensitive, so we'll just do our best based on that data, and we'll kind of circle in towards the optimal compositions.
So that's our setup right there. You can see right at the end. I just want to go back. It keeps going to this next video. I just want to show at the end what you're seeing on the video. This is Michael moving the magnet on a piece of whey paper, right? That's kind of like parchment paper.
Yeah, it's like wax paper.
And he's got this, the pieces are on here, and he's moving the magnet around. Now, what you also see in the scope is there's one speck of the LK99 stuff, which looks like it's diamagnetic. It's just spinning around in the magnetic field. It's not like attracted to it. And you see another little small fleck of a ferromagnetic material on the camera, which is actually, and this white thing you see moving around is actually the magnet.
Underneath the parchment paper.
That's the magnet moving under the parchment paper. So as you see the edge of that go near here, it moves around it lines up to the magnetic field.
Yeah, see, there's the magnetic particle.
But then you see this other little magnetic particle right in the center of the screen right now, and that gets attracted and pulled around by the magnet. You see when it escapes the circle of the magnetic field, it pulls it to stay on the magnet.
Yeah, and there's no such pull.
There's no such pull on the.
Yeah, you're just getting a torque to align with the field.
So that's why we said it's success and it's exciting results.
Well, and it may be pointing to the thing. It may be a ferromagnetic particle sort of like inside that.
That's
blob,
what we thought. But why does it move? Look at the way it moved right there at the end. It moves sideways to the field.
I suspect that's because of the angle of the whey paper, but we'll just have to see. But yeah, I mean this particle here, it looks like it's lining like a ferromagnetic particle would, but the particle is very non-homogeneous. It's not like a solid iron rod through there. It's like there's all sorts of stuff going on there. So there could be like a flat plate of material on one end of the rod or something that's doing this. It's weird. It's not definitely not a pure crystal of the stuff. Although at this point we have a few crystals that are a lot better purity that we could probably put under the microscope and demonstrate, and they definitely exhibit a diamagnetic effect. We should get that video up soon to
and then we're going to do another one. I want to do maybe we don't have time to do it tonight, or we have the conference starting here soon.
We should get this done with quick, and
so
well, let's get through the questions on the video.
Yeah, let's get through some more questions here.
Let's just scroll through everything. Let's see. In addition to ferromagnetic shaving, can you graphene? Oh yeah, we have pyrolytic graphite probably, and we can probably do something like that to compare to pyrolytic graphite.
Oh, so that wasn't the ideal way to create
paramagnetic spec.
It might be the reason they released the paper.
All right. Well, we have other specs that just kind of like that are thin, flat plates that just kind of lay on their edge. I mean, we have actually, at home I have some natural diamagnetic graphite we can compare to, but it looks very similar. Anyway.
Yeah, we should get some other samples just to show the difference.
Just to compare next to it. Yeah, that's a good idea.
That's good. That's a good suggestion.
All right, go up.
Anyone look, I'm still going down, so like if you have a question and there's a serious question, a scientific question, please repeat it as many times as you need to until we can see it and ask it.
We can go up in the earlier questions.
Yeah, but it's hard to find. There's a lot of questions here, a lot of comments. So
mainstream science reject it like they did cold fusion. Well, I mean, we'll see. I mean,
not if it can be replicated.
Yeah, if it can be replicated successfully, then we're fine.
Cold fusion still has some problems with replication and stuff, so, and consistency, and then net output.
Well, I mean, yeah, when you don't have a full understanding of what's going on, it's hard to
chasing the dragon's tail.
Did you try compacting the mixture to get higher density solid? That's a good question. Not yet. We can do that further down the line. Yeah, LK9
Yeah.
flux pinned.
Gold doping? No, we haven't tried that.
No, it's definitely not flux pinned. It just seems like diamagnetism or maybe paramagnetism.
We have some gold. And monatomic gold too, so we could probably try that.
Gold doping is tricky because it doesn't want to stay in the +2 oxidation state.
Yeah.
Also, the ion. So, I mean, a lot of people are comparing it to Ormus and stuff, but if this structure is superconducting because of the lattice strain, then gold is almost the same diameter as lead, so it wouldn't produce a lot of lattice strain. Yeah, we've seen the Salvatore Pais patent. We actually have some stuff set up. We're going to test that too at some point. And here's we got these piezoelectric plates, and these come coated with silver. So we're going to dissolve that off and replace it with
Yeah, we got these from
aluminum.
Salpais.
Nah.
Right? No.
So
not from Salpais, but this
he
is
recommended
what he recommended.
this. So yeah, you get a piezoelectric crystal PZT, and then you get the silver off of it, and you put aluminum on it.
All right, I thought you said you got them from him. Sorry. No.
Let's see. Where is this stuff? So the crystal you already made has enough to start. Yeah. So in theory, we can nucleate a larger crystal from the thing, but as we said, this material is very inhomogeneous, so it's hard to tell exactly where the crystal is within the block of material. I mean, you could kind of crush it down even smaller and just pick out the best pieces. Let's see, measuring the critical temperature. Yes, we're going to heat it up and cool it down and see if that affects the behavior. Does it need expensive equipment to make? Yeah, this furnace is like $8,000 or whatever. So yeah. I mean, as I said, if you have glass blowing equipment and a smaller, if you get like a JB Platinum vacuum pump, you can get one of those for like $500, and that'll get you hard enough vacuum. And then if you set that up with a glass blowing rod, you can pull vacuum on the glass, and you can blow ampules of this stuff, and then you can just put it in any normal furnace. I know there's like a tabletop furnace company has like $500 furnaces that you can get. So yeah, if you want to test this right now, you can do it for about $1,000.
Yeah, and that's the most expensive, those two pieces of
so
equipment.
I highly recommend that anyone who's got the extra funds for it, who wants to try it, go ahead and try it. I mean,
All right.
we need more data points on this. So,
well, we have the meeting too, so we got to go to the APEC team meeting.
I feel like we missed some questions further up.
I know, I do too.
Let's see. How are we keeping the lead metal vapor out of the air? Yeah, so at the moment, it's going right into our, what do you call the thing? It's going right into our vacuum pump, which isn't great for the oil either, but that'll cool it right down and solidify it. What else do we have here? Someone's calling us. Sintering could help with density. Yeah, I mean, you could sinter it, I suppose. Mark's calling us. We should get on the other call soon.
We're going to get on this. I want to wrap this up here.
Let's see if
what
there's
about a pottery furnace? Could you?
Yeah, pottery furnace will do. You would definitely want to have some sort of thermocouple measuring the temperature just to check.
Hey, we're still live.
I'm gonna actually, if I can go through all of these more. Let's see. Yeah, lead metal vapors. Yeah, I mean, and I don't recommend doing it that way. By the way, you should have a bubbler or something on the outlet of your vacuum furnace, especially if you have it running continuous. You can kind of like pull vacuum and let it sit for a long time, and then turn the vacuum furnace back on when you just start to see the needle slightly open up, because 10 to the -2 torr seems to work just fine. Co-precipitation of lead apatite. Yeah, I mean,
close that volume on that too.
Oh,
so that way it's not.
Thank you.
There. Anyways,
Okay.
We'll do another stream here in a couple days once we get some more things. It's just there's a lot of here's another. Is this Korea?
Crucial point is whether there's yeah, of course. I mean, it's only a matter of time, and it just takes time for crystal growth big enough to put a 4-point probe on it, and also definitive enough, because you need to make sure it's a single crystal that you're testing.
So that's the final. When do you think we'll have the final results? And what we're looking for is a piece big enough that we can put a 4-point probe on to test the superconductivity. And we're also looking for a test on the pieces we have to see if they lose the diamagnetic effect at a critical temperature. So we'll get back to you guys once we have the answers to those 2 questions and those 2 things figured out. Or at least
maybe within a month, I would say, for final. I mean, someone will know for sure whether this is replicatable in a month or so.
So thank you guys for watching. I hope you learned something. Michael's really hard to follow sometimes for people who are new to this that want just like a basic explanation.
I don't dumb it down. Sorry.
Yeah.
Everyone got to be like running to get on the same level. You know.
You got to run to get on the train. Okay.
So we gotta like save humanity here. You know. You got to be working harder than just sitting around playing video games or whatever. There's a lot to learn out there, and it's a beautiful world, and you learn more every day.
Yeah, so run fast and try to jump on the train, and hopefully you guys who are new and just got here can go rewind, put it on slow, and go and look up all the terms.
No, double speed. Yeah,
double.
Your brain can handle it.
Yes. Well, some out there can, but some of us need to sit there and Google half the words in your vocabulary so we can make sure they're real.
Fine. That's why I use them. So you Google them.
Yes, exactly. So thanks for watching, guys. I'm excited. Are you excited? I'm hopeful anyway. This would save humanity and be awesome if we could do this. And it's now about finding cheaper ways and better ways to produce it, so that everyone in their garage can make this stuff in their oven at some point. That'll be great.
I'll take care of some stuff.
Thank you guys for watching. We gotta run and jump on this call, so there's a whole bunch of stuff we got to do. Thank you guys for watching, and I'm gonna open this up for discussion. Thank you.